I will be doing video number 8C. A spring with a spring constant of 1,000 newtons per meter is compressed by 0.3 meters and an 8 kilogram block is placed against it on a frictionless ramp. When the spring is released, identify the forces doing work on the block after the spring is released. How far up the ramp, give distance along the ramp, not height, will the block travel before it stops? Don't use kinematics, use concepts of work and energy. So they give us this diagram. It's pretty much, there's a spring, the spring constant is 1,000. The spring is compressed 0.3 meters, shown right there, so that's 0.3 meters. And the angle of the ramp is 30 degrees, and the mass of the block is 8 kilograms. Okay, so what they want is to identify the forces acting on a block. So there will be the force of gravity downwards, the force of the spring going upwards or along the track, and then the force normal perpendicular to the track. Okay, those are the forces after the spring is released, and then it wants us to find how far the block goes up the ramp after the spring is released. Not the height, but the distance along the ramp after the spring is released. So we know all of this. We know Hooke's law is force of the spring is negative kx. The potential energy of a spring is 1/2 kx squared. And we know that work, because they want us to do it in the constants of work and energy. So we know work equals force times distance. Okay, so we know that work is force times distance, as stated before, but we also know that work is equal to the change in energy. And so we can make them equal to each other. So we can do force times distance is equal to the potential energy of the spring, which is the change in energy. So you would get, so the force would be the gravity, the force of gravity. But it wouldn't be just gravity, it wouldn't just be mg. There's components of gravity, and we would have to use the x component of gravity, which is the component along the track, which would be mg sine theta. And so I'm replacing d with l. It means the same thing. They're both distance along the track. So I'm just going to replace it with l. So it would be mg l sine theta, or pretty much the force of gravity in the x component, x direction, along the track, times the distance. Force times distance, mg l sine theta. And that's equivalent to the potential energy of the spring, which is 1/2 kx squared. And so when you plug in everything, you get, I'm moving L all the way to the left, so I plug in mass, which is 8, gravity, which is 9.81 meters per second squared, sine of 30, because the angle is 30 degrees. That's equal to 1/2 1,000, which is K 1,000, times 0.3 squared. That's how much the spring is compressed, 0.3 meters. And so you plug that in, solve for the distance, which is L, and you'd get 1.15 meters. And so the spring, that means that means the block travels up the ramp for 1.15 meters after the spring is released. And so this relates to what we've been learning in recent lectures and classes, because we've been learning about the potential, we've been learning about energy. And so springs have energy, the potential energy of spring. And so we use that. And we've also been learning about work, so we used work and energy to solve this problem, which is similar to what we've been learning in class. All right, thank you.